Hey students, Professor Nugent here. In the last video, we discussed implications of homoscedasticity and heteroscedasticity for standard errors, and we concluded that we should always use heteroscedasticity robust standard errors. If we use homoscedasticity only standard errors, and our data is in fact heteroscedastic, then we are exposing ourselves to type 1 error. That is, we are exposing ourselves to rejecting the null hypothesis when the null hypothesis is true, right? Because our standard errors will be too small. They will be incorrect. So that is not good. We want to make good inference, and so we should use heteroscedastic robust standard errors. It's quite easy for us because we're using theta, right? Comma robust after your regression. All right, in this video, we're going to discuss some additional theoretical foundations of ordinary least squares. We have already learned a great deal about OLS. OLS is unbiased and consistent. We've shown this. We have a formula for heteroscedasticity, robust standard errors. And we can construct confidence intervals and test statistics. What more could we possibly want? In addition to this, a very good reason to use OLS is that everybody else does. Okay, there are network effects here. So by using it, others will understand what you are doing. In effect, OLS is the language of regression analysis, and if you use a different estimator, you are speaking a different language. Sometimes it can be best to take the path that everybody else is taking. And if you veer off that path, you will have to explain to many degrees why you are taking that path. But still, you may wonder, is this really a good reason to use OLS because everybody else is using it? Aren't there other estimators that might be better, in particular ones that might have smaller variance, so that they might be more efficient? Also, what happened to our old friend, the student t-distribution? So let's answer some of these questions. In this video, we're going to look at when OLS is best and when there are other better estimators. In the next video, we will revisit our old friend, the student t-distribution. Before we continue on in showing when OLS is the best and when there are other better estimators, we need to add to our set of assumptions. We started with the first three assumptions, 1, 2, and 3, that the expected value of u given x is equal to 0, that xi, yi for I equals 1 through n are IID, and that large outliers are rare. Now we're going to add 2 more assumptions. 4, we're going to assume that the OLS residual u is homoscedastic. 5, we're going to assume that u has a normal distribution with a mean of 0 and a variance sigma squared. Now, assumptions 4 and 5, they are more restrictive. So they apply to much fewer cases in practice. However, if you make these assumptions, then certain mathematical calculations simplify and we can prove very strong and very useful results that hold only in the case that these additional assumptions 4 and 5 are true. So we're going to start with our discussion of the efficiency of OLS. And efficiency is referring to the size of the variance, which is the smallest. So the efficiency of OLS comes from the Gauss-Markov theorem. Under assumptions 1 through 4, we don't need 5 yet. So the basic 3 plus homoscedasticity, beta 1 hat has the smallest variance among all linear estimators. Okay, and estimators that we're thinking about estimators that are linear functions of y1 through yn, and this is the Gauss-Markov theorem. Now, the theorem, it is proved in the appendix, but this is not necessarily, we're not a theoretical course, we are an applied course, so I'm not going to push the theorem on you. But I would suggest that if you are interested in the theory upon which our work is built, then consider taking Econometrics 721 with me in the fall. So we do want to understand when the Gauss-Markov theorem applies and its result. So we need to look at all linear estimators, right? And so that means the following. Beta 1 hat is a linear estimator. That is, OLS is a linear estimator. That means it can be written as a linear function of y1 through yn. Recall how our expression of beta 1 hat minus beta 1 is given by this ugly looking thing here, that we have the sum from I equals 1 to n of xi minus x bar times ui all over the sum from I equals 1 to n of xi minus x bar squared. We can rewrite this as 1 over n times the sum from I equals 1 to n of wi times ui, where wi is equal to that. So beta 1 hat is linear in y. And Gauss-Markov theorem says that all possible choices of wi, the OLS weights yield the smallest variance. Okay? OLS weights yield the smallest variance. And the weight is, we're thinking about the wi. That's the weight. The weight on the residual. Okay. If we add the additional assumption that the OLS residual is normally distributed, then we get the result that beta 1 hat has the smallest variance of all consistent estimators, linear or nonlinear functions of y1 through yn. And this is a pretty amazing result. Okay, so this result says that if, in addition to the least squares assumptions 1 through 3, the errors are homoscedastic and normally distributed, then OLS is a better choice than any other consistent estimator. And because an estimator that isn't consistent is a poor choice, this says that OLS is really the best you can do if all 5 of the least squares assumptions hold. Again, we're not going to prove this. We will in ECO321, so if you're interested in the theorem, please join me in the fall. But this is a really useful result. I think it's a useful result because it shows the power of OLS, because it says that OLS is the best that you can do. It's better than any consistent estimator. But all 5 assumptions have to hold. So we have been talking up OLS in the last few videos. Let's point out some caveats here. There are important limitations. The Gauss-Markov theorem, it's not that compelling, okay, because the condition of homoscedasticity often does not hold. Homoscedasticity is a very special case of heteroscedasticity. Heteroscedasticity is typically what we're going to find in economic data. And the result is only for linear estimators, which is a small subset of estimators. we will work with nonlinear estimators later in the semester. The strongest optimality result, which is part 2 from above, not only requires homoscedasticity, but homoscedastic normal errors, which is not plausible in applications. If you think about hourly earnings data, you have a right skew in hourly earnings data, right? Hourly earnings data are not normally distributed. Finally, OLS is much more sensitive to outliers. Finally, we know that OLS is sensitive to outliers, and OLS is more sensitive to outliers than other estimators. So if we have not satisfied all of these assumptions that we've laid out, including outliers and homoscedasticity and normal standard errors, there may be other estimators which are better. In the case that we do have outliers, recall that the median is preferred to the mean as an estimate of the central tendency of a distribution, right? So if you have a long right skew, as with earnings data, you may find that the mean is right about here, and the median may be somewhere closer to here. So the median is typically a preferred measure for the central tendency of a distribution in the case that you have a long right tail or a skewed distribution of any sort. Similarly, in regression, because OLS is sensitive to outliers, like the mean is sensitive to outliers, if you have big outliers, other estimators can be more efficient, which means they can have a smaller variance. And one such estimator is the least absolute deviations estimator. This one right here. Okay, and so what we see here is that the absolute value of the prediction mistake is used instead of the square of the prediction mistake. And this puts less weight on the outliers by using the absolute value instead of the square.